All right, so to start off with, we're going to look at the language that we use in proofs, that is the language of logic. So it all starts with a proposition. Okay? And a proposition is simply a sentence that proposes something. And it might be true, it might be false. Okay, so it's either going to be true or false. So an example, it is raining. That's a proposition. So it is raining. It might be true, it might be false. As opposed to, is it raining? That's not a proposition. That's a question. So logic, it has its own language that we use when we set out our logic. It consists of propositional variables, and they tend to be just pronumerals. Often you'll see things like P1 for proposition 1, P2 for proposition 2, or they might just lose letters, X, Y, Greek letters, it doesn't matter. Punctuation symbols. So just like our regular language, it has punctuation symbols, but usually the punctuation symbols are actually the parentheses. Open parentheses, close parentheses. Then you have logical symbols. They're the connectives, and that's what joins the propositions together. So the right arrow, that's the implication symbol. And we use that for if-then statements. The, I don't know what you call it, a hook or a...
Tilde.
No, I'm not talking about the one in parentheses. I know that one's called a tilde. Anyway, whatever that thing's called. Okay. It stands for negation. So it's the complement of a proposition. Now, if you've got the arrow that's going in both directions, equivalence. So you're talking about two propositions that are logically the same or logically equivalent. That stands for and. It's very similar to set notation, of course, and would be intersection, wouldn't it? So it's got that sort of shape to it. But so it's the conjunction of two propositions, and or, again, very similar to set notation, where we have the U shape for union, but it's the disjunction of two propositions. And then we have our quantifiers. So the backwards E stands for there exists. And then we have some people call it an upside down A. Some people say it's a V with a bar across it. But that stands for all. So statements. A statement could be simply a proposition in itself. Or it could be several propositions that are then joined together by connectives or symbols or what have you. So what's a logically valid argument is when you have a list of propositions and then a conclusion follows those. In other words, that's a proof. So think back to, I guess, the first type of proof you did, and that would be in geometry. Well, you had a list of propositions and then you concluded your proof. Now, this is not an example of a logically valid argument. I'm now actually defining example. Okay, so example is a situation that demonstrates the assertion of the proposition, which brings us to counterexample. Counterexample tells us the proposition is not true. That can be very useful, a counterexample, because if we want to invalidate something, all we need to do is find a counterexample. Doesn't work, therefore the argument becomes invalid. All right, negation. So if you want to negate a statement, to negate it, it will change its value. Remember we said it's either going to be true or false. So it'll change true to false or false to true. Now, some rules here. If you want to negate X and Y, it's the same as saying negation of X or the negation of Y. And the other way around works as well. If you're going to negate X or Y, it's the same as the negation of X and the negation of Y. All right, look at this one very closely. The negation of, for all X, AX, or whatever the situation is. Right, so for all X, this statement. If you're going to negate that, that would be the same as saying, hang on, there exists an X where it's not AX. So the negation of, there exists an X such that AX would be, for all X, we don't have AX. All right, so here is my proposition. The number is even. The number is even. So if I had the number 6, that would be true. That would be true. If I had the negation of x, now the negation of x is not the number is odd, because you can have other numbers as well. You can have fractions, for instance. So the negation is the number is not even. 6 would now be false. So the negation has turned the true into a false. All birds are black. The negation of that would be at least one bird is not black. Or another way I could write that is not all the birds are black. Or maybe some of the birds are not black. I mean, there's lots of different ways you could say it. Now, let's have a look at this. Here's my statement. There exists an x which belongs to the real numbers, so is an element of the real numbers, such that x squared is less than 0. Now remember I said a statement can be true or false. In this case, it's false, isn't it? But the negation of that would be for all x that are elements of the real numbers, x squared is greater than or equal to 0. That would now be true. Yeah, because the colon stands for such that. So when you go there exists, you're saying there exists numbers such that this condition happens. Whereas the other way, you'd have a comma because you're not saying such that, you're just saying for all x, this happens. Let's have a look at implication. So these are our if-then statements. P implies Q. So if we have P, then we have Q. So if P is true, then Q must also be true. Because we're saying whenever we have P, we have Q. So P implies it. P is what we call the premise. So it's the premise of it. Q is the conclusion. So again, if you go back to proofs and what you were doing in geometry, you were making, several premises. Because you might be saying, these angles add up to this, and you might end up with a conclusion, therefore the shape's a triangle, or something like that. So P implied Q. The fact that I had all these bits of information, I could conclude this statement. P is called a sufficient condition. And it's a sufficient condition. Why do we call it a sufficient? Because Q can still exist without P. P implying Q doesn't mean that if I've got Q, I've got P. It means if I've got P, I've got Q. So if P exists, Q must exist. So in other words, P is a sufficient condition to conclude I've got Q. Q is a necessary condition, however, for P. P cannot exist unless Q exists, because we're saying P implies Q. So every time we've got P, we've got Q. So if we don't have Q, we can't have P. An example of that. Let's have the X will be you will score 90% or above in extension 2. Y is you always listen to your teacher. So X implies Y. Well, scoring 90% or above is sufficient to conclude that you always listen to me. However, it is necessary, it's a necessary condition that you listen to me if you want to score 90% or above, okay? Now, remember I said they could be true or false. This one is, of course, true. Now, the negation of P implies Q would be that you have, so the equivalent statement is you have P and you have not Q. Because remember we said every time you have P, you have Q. So the negation of that is we have P and we don't have Q. Converse. It's like the reversing the implication. So the converse of P implies Q is Q implies P. So that's the converse. Now, you might have a true statement. It does not mean the converse is true. And similarly with false, you might have a false statement, but the converse is not necessarily false. Let's use this one. X is, it is raining. Y is, the grass is wet. It might well be true that X implies Y. If it's raining, then the grass is wet. That's a fair argument. It's not necessarily true that Y implies X. Just because the grass is wet does not mean it is raining. Someone might have turned on the sprinkler. Equivalence. They're our if and only if statements. You remember the first time you saw IFF and you thought, I misspelt it. No, I haven't misspelled it. If and only if is IFF. So P is equivalent to Q. And they're the ones where both ways are correct. So the statement's correct, but also its converse is as well. It reads both ways. Example, X, A, B, C, D is a parallelogram. And our other statement is the diagonals AC and BD bisect. So we have got X implies Y and Y implies X. Right? If the diagonals bisect each other, we talk about quadrilaterals, of course, then we know it's a parallelogram. But if it's a parallelogram, we know the diagonals bisect each other. So it reads both ways. So X is equivalent to Y. They are equivalent statements. So the way we wrote it in geometry is something like that. Well, ABCD is a parallelogram if and only if the diagonals bisect each other. So it read both ways. Now, this might be a new one. Contrapositive. Contrapositive. The contrapositive of our implication is when you negate the converse. So you negate the converse. So if the original statement is P implies Q, then the contrapositive statement is not Q implies not P. So negating the converse. And they are equivalent to each other. So sometimes if you're asked to prove that P implies Q, it can be easier to prove that not Q implies not P. And if you prove that, then you can say, oh, hence P implies Q by contraposition. They are indeed logically equivalent. Here's an example of that. X is going to be the statement, a polygon is a triangle. And Y is that the interior angle sum is 180 degrees. So X does imply Y. If a polygon is a triangle, then we know the interior angle sum is 180 degrees. Well, let's have a look at not Y implies not X. If the interior angle sum is not 180 degrees, then we know the polygon is not a triangle. So they are actually equivalent statements. Now, truth tables can be really handy in proving things. Not actually in the syllabus truth tables. I do not understand why. But as I say, they can be useful ways of proving something. So we have PQ. Well, let's have a look. Let's, for the sake of showing you how we work a truth table, P is going to be the statement, the cat is white. Q is going to be the statement, the dog is black. Each of those statements could either be true or false, so we have 4 situations. We could have a situation where both are true. Now, if both are true, then the negation of P would be false. The negation of Q would also be false. But now, P or Q would be true. Because remember, we're assuming both of these statements are true. So it is still true to say that the cat is white and the dog is black. Because we're saying these are both true. So that is still a true statement. The or statement is still true. The cat is white or the dog is black. That's still true. P implies Q. If the cat is white, then the dog is black. Well, that works. Because, again, they're both correct. And they're equivalent, so that's true as well. But what happens when Q is false and P is true? So the cat is white, but actually the dog's not black. So the negation of P will now be false. P and Q will now be false, because you don't have both. P or Q is true, that hasn't changed. P implies Q is false now. Because remember we said, whenever we have P, we must have Q. But we don't now, because we're saying P is true, Q is false. So P implies Q becomes false, and they're no longer equivalent. They do not have the same value anymore. One's true and one's false. So that would be false. What about the other way round? If P was false and Q was true, so the negation of P would be true. P and Q would be false, because they're not both correct. P or Q would be true. P implies Q is now true. Because remember we said that Q could be true, we don't necessarily have to have P. So that's now true, but the equivalence is now wrong. If they're both false, then we would end up with, well, the negation of P is now true. P and Q is false. We don't have either of those statements. P or Q is false. P implies Q will now be true. We don't have P and we don't have Q. And then P equivalent to Q, that is true as well, because they're both taking on a false value. This is where it's a little bit different because, by the way, I haven't put the answers on your sheet. You're going to have to work it out. So, Alfred, Kurt and Rudolph are accused of stealing and selling copies of an exam. At the inquiry, they testify as follows. Alfred says Kurt is guilty, but Rudolph is innocent. Kurt says, well, hang on, Alfred's guilty, and so's Rudolph. But Rudolph says, hey, I'm innocent, but at least one of the others is guilty. What you have to work out, can everyone be telling the truth? Is that possible? If everyone is innocent, who lied? Someone must have lied. And assuming everyone is telling the truth, who's the guilty person? Oh, there's a fourth one? There we go. If all the innocent people tell the truth, and the guilty lie. All right. So these were our three statements. I'm going to say A is the statement, Alfred is guilty. K is the statement, Kurt is guilty. R is the statement, Rudolph is guilty. And I'm going to draw up a truth table. Yes. There's 8 possibilities. They could all be true. So what we do in maths with things like this is we reduce basically a language argument, we turn it into maths using our rules. Now, Alfred's statement was Kurt is guilty and Rudolph is innocent. So we have K and we have not R. Well, K. We're saying, well, K, I just copy all the K values down. True, true, false, false, true, true, false, false. Not R, I change the values. So I go false, true, etc., etc. And then what was our rule for and? Because the only true values will be when we have true and true. Let's have a look at good old Kurt. Kurt's one is that Alfred is guilty implies that Rudolph would also be guilty. So plug in the values for A and R. Now, A implies R. The only ones that were false were true implies false. So all the others are true. Now for Rudolph, his was a little bit more complicated. We have not R. So Rudolph is innocent and either A or K. Put in the values for A, K, and we negate the R. The parentheses, just like in maths, we do the inside first. So first of all, we have a look at that that or, A or K. And when we had A or K, it was only false and false that became false. So the bottom two are false, the rest are true. So now I'm looking at that blue column and I'm matching it up with the not R. So we have not R and the blue column. So and the only ones that were true and true, so they become true and the rest become false. Now I should be able to then answer the questions. Can everyone be speaking the truth? Now remember, A, K and R are not what they're saying. These red ones are what they're saying. So we're looking for, is there a row where all three are true? And there it is. So yes, it is possible that they all could be telling the truth. If everyone is innocent, who lied? So if everyone is innocent, that would be our false, false, false. So who lied, going along that line? Well, it's Alfred and Rudolph that have come up with a false statement. Assuming everyone's testimony is true, who is the guilty person? So now we're looking at the red ones and we're saying, looking for the line where all are true. So who are the guilty ones? Yes, as we suspected, it was Kurt. All right. And the fourth one, if the innocent tell the truth and the guilty lie, who is guilty? So you sort of got to look at both of them for this one, but that's the row right there. Okay? The innocent tell the truth and the guilty lie. Who is guilty? Well, Alfred and Rudolph turn out to be guilty on that one.
But the innocent tell the truth and the guilty.
The innocent tell the truth and the guilty lie. 2A. All right, that's